Find the current ID using LCM equations of this PMOS transistor. We are given the following parameters. Threshold voltage equals negative 0.4 volts. Transconductance parameter Kp equals 1 milliamp per volt squared. Bulk threshold equals 0.2 volt to the 1/2. Channel length modulation equals 0.1 volt to the negative 1. Oxide capacitance equals 1.004 microfarad per centimeter squared. Surface potential equals 0.88 volts. Width equals 1 micrometer. And length equals 0.1 micrometers. So, starting off, we need to identify all 4 parts of this transistor, starting with the gate on the left here. And since this is P-channel, on the top we have the source, and on the bottom the drain. It's the other way around for NMOS. And on the right we have the body, which is also known as the substrate, which is connected to the highest potential of the system, which we are given to be 3 volts. Starting off, we need to see whether or not the device is on or off. The voltage VSG determines this, which equals Vs minus Vg. And at the source we have 2 volts. At the gate we have 1 volt, and the difference is just 1 volt. This must be greater than negative VTP, the threshold voltage of the P channel, which may incorporate the variable VTPO if body effect exists. So we need to see first if body effect is prevalent, where VBS equals VB minus Vs, which is 3 volts minus 2 volts, that's 1 volt, which shows that there is body effect. If there's body effect, we need to modify VTP, which now equals VTPO minus gamma times the square root of absolute value 2 phi f plus VBS minus the square root of the absolute value of 2 phi f. Plugging in the numbers, we get VTP0 of negative 0.4 volts minus gamma, which was 0.2 volts to the 1/2, times the square root of 0.88 volts, plus 1 volt for VBS, minus the square root of 2 phi f once more, 0.88 volts. Closing the brackets, we get a VTP equal to negative 0.487 volts. Again, it's negative since this is P-channel. And VSG must be greater than the negative value of VTP so that the device can be on. VSG, again, equals 1 volt, and that is of course greater than negative VTP, which we just found to be 0.487 volts. Thus, we can conclude that the device is on. Moving on to the mode it's operating in, we need to find the value VSD sat. And if VSD is greater than this value, it is in saturation region. Else, if it's less than this value, then we are in linear or triode region. So, VSD sat, according to LCM equations, is VSG plus VTP, which we found earlier to be 1 volt minus 0.487 volts, which is 0.513 volts. Comparing this to VSD, which is Vs minus Vd, or 2 volts minus 1 volt, which is again 1 volt. VSD is greater than VSD sat. Since that is the case, we are operating in saturation region, which will give us our current formula. I'll call it ID sat. We'll say that this is ID. And this equals Kp over 2 times parentheses VSG plus VTP quantity squared times 1 plus lambda times VSD minus VSD sat in order to account for channel length modulation once more. Plugging this in, we get 1 milliamp per volt squared, or 1 times 10 to the negative 3 amps per volt squared to get standard units. Divide by 2, don't forget to do that, times 1 volt minus 0.487 volts squared times 1 plus 0.1 volt to the negative 1 times 1 volt minus 0.513 volts, closing the parentheses twice. And finally, after putting that in the calculator, you get an ID sat equal to 138 microamps. And that's everything. If you have any questions, please leave in the comments below, and good luck.